So a force X graph, X-axis, and then you have like something like this. You know, the force is variant, and so you do your area under your curve, and so the way that you find the work here is doing the integral between the two limits. You know, initial position to final position, f dx, where you just integrate over x. So this would be that situation only if the work is, or the force is variant. Typically we look at the forces that are constant, so it makes our lives easier. So, and that's just going to be just, you know, just particular importance to the calculus people here. But again, I don't see that a lot, but this is something to be aware of, how you would perform that operation and getting the work done by a varying force. Just to throw that out there. So it's kind of, we've already been implicitly doing that already just by saying F delta X, you know, but the force is constant. But when we have a variant force, we have to do it a little bit differently. So then the next part is work done by a spring. This is Hooke's law. K delta X, they listed as Kx. Same. It doesn't even matter at this point. You understand that there's going to be a displacement. So Fx or Fs for the spring force, and this is just the spring force along the x-axis. And so you know that K is your spring constant, delta X is your displacement. Okay. So nothing much about that. I'm not going to go through the derivation of Hooke's law. It's not that important. We understand that, or the derivation of the work by a spring. Just going to give that to you at this point. I'm just going over the equations and basic concepts. So the work done by a spring, 1/2 K delta X squared, which is just the integral of force. So it's a spring potential energy, if you will. Work done by the spring, which is the potential energy of the spring. It's really the same thing. So there's your spring potential energy, 1/2 K delta X squared. The work kinetic energy theorem. And I suggest to you, like, you can just go to the ends of every chapter and just aggregate all of the equations together into a nice, you know, equation sheet just to kind of review and practice. You can definitely use that in our practice exams. And there's also equation sheets that'll be provided not only on the exam, but it's on the practices. So hope you're just going to access those as soon as possible, or write these all down as we're doing here and put them together however you want. But at the end of every chapter, there's just a kind of like a list of all of the relevant equations. Okay, so we know that work is F delta X. If we're just doing horizontal work or horizontal pull on the x-axis, this F delta X is going to be equal to a change in kinetic energy. We are moving the object from rest to a final speed, or moving it from one initial speed to a final speed. We're changing the kinetic energy. Kinetic energy is 1/2 mv squared. And so then delta KE is going to be that equation there. So we're changing the kinetic energy from a final velocity to from initial velocity to a final velocity. And so all of those equations are equal. Work is F delta X equals change in kinetic energy. We also know too that when an object is falling, the work done by the force of gravity is going to be positive, okay, because the displacement delta y and the force of gravity are in the same direction. The angle between these vectors is 0. They're parallel to each other. So the work done by gravity will be positive, which will be exactly equal to the negative change in gravitational potential energy, which in turn is also equal to the change in kinetic energy. We'll be losing potential energy, gravitational potential energy, and gaining kinetic energy as the object falls from a height down, say, to the ground or to another position. And then if we raise the object into the air, obviously we're going to be losing kinetic energy at this point, because it's going to, at this instant, the speed is 0. And so we start off at a large speed, but then, you know, we lose it at this point. So, and then also the work done by the force of gravity will be negative, which in turn is going to be equal to the positive or increase in gravitational potential energy, and which in turn is equal to a loss in delta KE. Because at this instant, you know, relative to this moment, the final kinetic energy will be 0, because the final speed is 0 at this point. So 0 minus whatever it was, negative. So it's just the opposite, vice versa relationship. So this is a falling case, and this is a rising case. And so for this scenario, force of gravity is downward and vertical displacement is upward. So that's a negative work. The vectors are 180 degrees displaced or apart from each other. All right, so that just leads into the potential energy. We know what kinetic energy is there. Potential energy, or gravitational potential energy, mgh, commonly mg delta y, whatever. It's the energy relative to a vertical displacement. And you can choose any point in your system to be a reference level. So the gravitational potential energy is always with respect to some 0 point. So let's say that you are at the ground and that's your initial position, make that 0. And you go up to final position here, which is not 0. And you're increasing potential energy in the system. And then not only this, you can talk about this in terms of the delta KE or delta PE, which is going to just be final potential energy minus initial potential energy. You can also talk about the potential energy at each of the points, which basically what we're doing here. So at this point, this is going to be final, and this will be initial. The difference, the delta, will just be what, the difference in the potential energies at those moments. So this is kind of like, this equation here is just what is the potential energy at that point? And delta PE is just the difference between the points. And you can make any of those points 0. That's what's called the 0 level or the reference level. You can make anything a reference. You are referring to this point, whatever that point is, as 0. And relative to that point, you can define your potential energy. Any questions on that? It should be very easy for you. Back over those definitions. And so, like I mentioned before, if you define the top to be 0, that's your initial point, and come all the way down, Y final will be negative, whatever. Let's say if this was 10, this will be negative 10. So the change in potential energy will be the same because those positions are the same, but the weirdness, if you will, is here because now you're defining this height as 0. This is your reference. You can make anything to be 0, but this will always be constant. All right. We talked about elastic potential, which is 1/2 kx squared. Conservative, and non-conservative forces. Non-conservative forces, friction, air resistance. Conservative forces, gravity, gravitational force, force due to gravity, the electric force, the magnetic force. Conservative. So in those conservative force fields, our energy is saved. That's where we get our conservation of energy and momentum under the power or in conservative force fields like gravity. So you can take a look at some of the properties of conservative forces, page 182. Talks about conservative forces. The work that's done there, the work that's done in a conservative force field is independent of the path. So if you start at the top here, you go to the bottom, and you do something like this, the path is unimportant. It's all about the points. Final minus initial. makes our lives easier. When I talk about distance, we're talking about displacement, which is the difference between the points. And so if you go this way in your displacement, go downward or upward, the work is going to be constant. So this is a closed path. So we're closing this path off from the environment, and the work that's going to be done over this path is always going to be the same. The energy will never change between those 2 points. And if we define any other 2 points and we make another closed path, that work will also be constant. Which goes back to our discussion of conservation principles, conservation of energy, conservation of momentum. Whereas with the non-conservative forces, depending on, it doesn't matter what path you take, you're always going to lose energy. So friction will always take energy out of the system. Just to keep that simple. You can never recover the work that's done by friction. Okay. All right, I'm going to go and come back to the discussion on the potential energy functions, because we're all together and some of us are not going to be seeing that. So we go back to again on breakouts. I'll come back to that briefly. Anyway, going on to chapter 8. Conservation of energy. So in a closed system, say between two points, say we're falling. Let's keep this simple. Say y initials 10 and y final 0. And we're falling. We note that the negative change in gravitational potential energy is going to be exactly equal to this, the increase in kinetic energy. So the overall energy, or the sum of the changes, is going to be equal to 0. So that means that delta E is 0, which means that there's no change in the energy in the system. And we get that from basic definition of mechanical energy, which is the sum of potential and kinetic energy. So delta PE plus delta KE is delta E. So this just means that the energy is constant. There is no change, which means that the energy in a closed system is conserved. This goes back to our other discussions. And we can see that on page 199. So We know the changes are just a final minus initial. And then we just put all of the initial terms together and the final terms together. So the initial energy, the initial mechanical energy, technically, is equal to the final mechanical energy. From closing everything off to an environment, whether you're rising or falling, the sum of the changes in the potential energy, gravitational potential energy, and kinetic energy will be equal to 0. There's no loss. You're just changing the form of the energy from one to the other, from potential to kinetic, kinetic to potential, back forth. The amount never changes. When we introduce friction, of course, we're going to get some loss. So this conservation equation, in terms of friction or a non-conservative force, work done by a non-conservative force is going to be equal to this here. And so usually, kinetic friction mu k and delta x. So the force of friction times its displacement is going to be equal to this stuff. So we're going to get a loss in some of the energy due to deformation of the object, in terms of the heat, in terms of sound, different forms of, different circumstances are going to result in a loss of heat, a loss of energy from that closed system when we introduce friction. So this is a non-conservative case. And the top here, conservation, the sum of the changes equals 0. Delta E 0 is constant, no change. And then we got to change. Due to this term. Okay, so chapter 8 is mostly conservation, situations involving kinetic friction, more detail on kinetic, work done by kinetic friction. And as we wrap up chapter 8, talk about power, which is a rate of change of energy. It's primarily calculus based with dE dt, which is the same thing as delta E over delta T, all of you algebra based ones out there, which is basically work divided by T. So the basic in most physics textbooks, you got this, work over time. How much energy are you using in a certain amount of time? The rate of change of E. But don't get bogged down in the jargon. This is it. It's power. So it's going to be joules per second, the units, which is watts, James Watt. Units of power. So they go on, and they do their little magic stuff over here, and summarize it, of course. And we have power is work over time interval. Change the time. F delta x, delta t. Well, we know this way back in chapter 2, that's velocity, so force times velocity. another way of relating power. When you know force and velocity, you can get power. At work over time, you get power. Same thing. And this delta E could be your change in kinetic energy, which is work, or the magnitude of the change, if you will, of potential energy, delta PE over delta T. Because power is a scalar, and so we're going to talk about how much E, not a direction. Power is not a vector, it's just a number. So we have delta PE, the magnitude of the change, because we understand that PE can be negative, but our job with physics is to take the physical situation and relate it in terms of what's going on. We have to reflect the equations to the actual occurrence. And we can do delta PE because we're talking about a number that we're going to, the electric company is going to come by and look at the number of energy, watts or kilowatt hours that you're using, and look vectors, or obviously. So we're can relate power in terms of magnitude of the change of PE. So all these are equal. So there you go. And we know this because work is delta KE, delta PE. Then before watt came around, and power is measured in horsepower, which is 746 watts. And then we have what I was talking about before, kilowatt hours. So basically 1,000 watts in, 1 hour gives me a kilowatt hour. And then so we can go even further with this. Joules per second. And we have 1 hour, 3,600 seconds. So that proves to you this kilowatt hour that the electric company reads is unit of energy. It's not a unit of power. So it's 3.6 times 10 to the 6 joules for 1 kilowatt hour. And then based on where you live, there's a certain rate, so it's a certain amount, 0.08 cents per kilowatt hour. And they look at your kilowatt hours, multiply that, and they give you a bill. Okay. Onto momentum. Very basic. Momentum, P equals mv. It's vector, mass, v velocity. And it's basically another way of looking at Newton's first law. This object it's moving along with a constant velocity, has a certain mass. You can calculate its momentum. The units, kilogram meters per second. Then if we have a force in a certain amount of time to change the object's momentum, so say for instance it was moving along, P equals mv, then you have, let's say, a puck, hockey stick comes in and changes the initial velocity to It's a larger velocity. Right? So now we have a force comes in to change this momentum. Certain amount of time. Well, this all just comes from MA, which is M delta V over delta T. And just goes back here. So when we have, we're just taking Newton's second law and rewriting it in terms of our new concept of momentum. Let me just rewrite that. So obviously, if momentum is mv, this would be delta p, delta t. And then when you multiply the time on both sides, we get a concept called impulse. Impulse is basically a change of momentum. It takes a force in a certain amount of time to change the momentum of the object. Baseball bat on baseball, hockey stick on hockey puck, ball bouncing off a wall. That time of impact for this force of the wall or the baseball bat or the hockey stick changes the object's momentum. And this delta P is M delta V, which is final minus initial velocity. So those are all the same, and we can write the term of impulse by capital I. Those are all equivalent expressions. Equivalent expressions. So, yep. So that's section 9.2. Okay. So much more I can get here. Tomorrow. So if we have a bunch of objects that are colliding with each other, all of the forces important in that system is just the internal forces of the collisions. So these objects are rebounding off, just going back and forth. All these equal and opposite reactions. This guy is hitting this guy over here, going back and forth. And all the collisions are internal. So the net force in that system, the internal net force is going to be equal to 0. And so as we look at all these collisions and we close it off from the outside environment, just as a test case, we're trying to see what's going on with the system. We know it's not going to have any influence from the outside. So the net external force would be 0 in this case. So the total momentum inside this system, the change in momentum in this system will be equal to 0. And so from this idea, we get, conservation of momentum. We have the momentum of any two objects or any set of objects in the beginning will be equal to the momentum in the end. And so I have a little time to write that again. So let's say we have two objects and force of the first object on the second object is going to be equal and opposite to the second object on the first. And so we have this net force of 1 on 2 is going to be equal to 2 on 1. So then you can say the M delta V or T. So we understand that on the left-hand side, that this is object 1 on 2, we'll just call it 1. And this is 2, because this is 2 on 1. This is object 2 on the other guy, 1 on the other guy. So just say 1 and 2 at this point. So these time intervals are the same. So the collision, the time of impact is equal. So we get delta V1. So we know this change is going to be the final 1 minus initial 1 and 2 final 1. 2 final minus 2 initial. So you see where it's going. Okay, thank you. And then we have negative MV2 final plus MV2 initial. So like we did with the energy terms, with the initial terms of momentum on one side and then the final terms on the other. MV2 V2 final equals 1 V1 initial plus, so the sum of the momentum, so in this case there's 2 objects, could be 10, any number of objects. The momentum in the beginning stage is equal to the momentum in the final stage. So we have P final equals P initial. So the momentum of the system is constant, it's conserved. Okay, so again, this is this old hat, conservation of momentum. All right. Let's see. And we can also see this if we, so we know this is the case. Initial equals final momentum. And then here we can see that the momentum is constant. If we just take this here will be a change of momentum of object 1, times cancel out, is equal and opposite to the change of momentum of object 2. So as object 1 hits object 2, the changes of momentum in that system is going to be a constant. So no matter where 1 goes or where 2 goes, the sum of the changes will be equal to 0. Which means that there's no change, and we're just looking at those internal forces. We're closing it off from the environment. And so those forces that 1 puts on 2 and 2 puts on 1 will be equal and opposite. They'll be the same. And when you add those up, those are equal to 0. Which means that the sum of the change of momentum will be equal to 0. So if we just take this further, delta V1 equals negative V2, because we cancel out the times. And this is delta P1 equal and opposite delta P2. And then if you add them together, so that's why you get this sum of the changes. Right? So the momentum of the system does not change. All types of collisions, elastic, inelastic, all types, yes. Because no matter what kind of collision it is, the momentum will always be a constant, but then our energies, can change. So like we have two types of collisions, the perfectly inelastic and the elastic. So we have two objects cruising along. One could be at rest. And when they collide, their masses stick together and they move as one. So in a perfectly inelastic collision, which this equation relates, tells me that the momentum is saved, but the energy will not be saved, because some of the energy is going to get lost in the collision or in the sticking together, deformation of the objects if you have a car crash. So momentum will be saved, but energy will be lost. So that looks like this. That's not going to be, so VF squared, and out of space. So those two masses will have one common speed, and we know that the energy will be different on both sides. Momentum will be the same. For a perfectly inelastic collision, the elastic collision case is just the typical conservation momentum equation. So and so the energy and the momentum is saved in the elastic case. Spare you the writing of the kinetic energy equation there. All right, so to wrap things up, we'll talk about a little bit on the impulse graph of force versus time. So we have, let's say we have, so we have force versus time. So we normally look at impulse in terms of an average force, that our force is constant. So let's say we have some average force, and if we wanted to find the impulse, we just find the area under this particular curve. But in reality, the force actually changes. Like when you are hitting a bat on a baseball, so that initial point of contact is going to be very small, and then as you go through the swing, the force is going to peak, or the contact is going to be maximized, if you will. And then as you complete the swing, the baseball starts to leave the bat, and so the force goes back down as the ball starts to travel away. So in that time interval, we have a situation, something like this. So we have a maximum force and then back down to a minimum. So in reality, we'd have to, take the area underneath this curve, integrate this function to get our true impulse. But for the most part, we're looking at averages. Whereas in reality, I can just superpose these. In reality, it's really that situation. So, if you will. So we keep our life simple with the average force. So that's about it. That's about it for today. Continue tomorrow and center of mass, talk a little about that and keep on going forward. So that is it. Any questions? It should just be, just reprising old stuff. All right. That's it.